Andrew Carnegie started out wanting to set up an institution to support amazing individuals to explore science in the most liberal way. So I think it's very natural for our science to really converge on the origin topic.
Certainly the origins of life is probably the most important question for all of us to understand, right? It's where we came from. The real ultimate thing, of course, we're very interested in is, are we alone? I think that's the biggest question we could ask. Is life very common in the universe? And to understand that, you really need to understand where life comes from. And so understanding the conditions that led to life here on Earth is important to understand that generally.
Ever since the early 1600s, when Galileo used the first telescope to look at the stars, or look at the solar system, and saw craters on the moon and spots on the sun and moons orbiting Jupiter, we realized that the heavenly bodies were not divine and ethereal, but were probably made out of the same kind of stuff as on Earth. And immediately in the early 1600s, people began speculating about life elsewhere in the universe. And there's no question that is more profound than whether life exists elsewhere. The Origins project of the Carnegie Institution will address all of these questions in 4 sessions. Tonight is the inaugural session on the formation of planets. We have 10 distinguished scientists who will speak to you tonight. So now let me welcome our wonderful scientists to the stage.
Well, the most exciting development that I can think of in exoplanets would be some telescope, space telescope or ground-based telescope that could directly image planets around other stars. And we may be able to do that with 30 to 40 meter ground-based telescopes within the next decade. So that's very exciting.
And what I want to do is just talk really briefly about what it takes to have a habitable planet. So let me just start out with some of the most fundamental requirements for life. This won't be a complete list, but the ones that I think are most important. First of all, you need a planet with either a rocky or a liquid surface. You have to have some kind of interface there where life can get started. So we don't think gas giants are a good place. Second requirement that I think is fundamental is that you have to have carbon. Life on Earth, of course, is carbon-based. Carbon forms long chains because it can form 4 bonds. I read a lot of science fiction growing up, and science fiction authors like silicon, too. Silicon is right below carbon in the periodic table, and so in theory, you might be able to do the same kind of chemistry with silicon, but silicon bonds strongly to oxygen and forms things we call rocks. And it's very difficult to get them unbonded, so I don't think that silicon-based life is likely. The third requirement, which is an absolute requirement for life on Earth and may be a requirement elsewhere, is that you need liquid water. The other thing that I'm going to be specific on is I'm most interested in planets that have liquid water on their surfaces. And why is that? It's because, I'm interested in the search for life on planets around other stars. If the water is present on a planet's surface, then that life can be in contact with the atmosphere and can modify the atmosphere in a way that's detectable from a long distance. So this leads to the concept that I've worked on and off for many years of the habitable zone, which is shown by this blue strip in this diagram. It's stellar mass on the vertical scale and distance from the star on the x-axis. You can see that the planets of the solar system are shown there with Pluto x'd out because Pluto got deplanetized a few years ago. These days, we like to plot the habitable zone a different way, and so this is a way that sort of blows up the habitable zone region. So now instead of stellar mass, we're plotting stellar temperature on the y-axis, and we're plotting the amount of sunlight received by the planet compared to Earth on the x-axis. So you can still see, if you look up at the top there, you can see Venus, Earth, and Mars. There's a conservative habitable zone that comes from climate models. There's an optimistic habitable zone that comes from observations of planets in our own solar system. And then if you look carefully down at the bottom, you will see Proxima Centauri b that Guillaume discovered a couple of years ago, and also 4 of the TRAPPIST-1 planets, 3 of which are in the conservative habitable zone and 1 in the optimistic habitable zone. So the big goal over the next, say, 20 years is to build some big telescopes that can actually find these planets and take spectra of their atmospheres. Thank you.
One of the things that I think about is icy moons, and NASA is going to be sending a spacecraft to Europa, one of the moons of Jupiter. And I don't know what it's going to find. I think it would be enormous to know that we're not alone in the universe. That would be very exciting. Jim gave a very elegant introduction to the concept of habitable zones. What I want to talk about is, at least in this solar system, thinking about habitable zones in the traditional way may actually be a bit too restrictive. And so this is a diagram similar to what you've seen before. If you're too close to the star, then you end up too hot like Venus. If you're too far away from the star, then you end up freezing like Mars. And somewhere in the middle, there's this sweet spot where the Earth happens to sit. But in this solar system, we know that the gas giants and the ice giants outside have moons. They have satellites. We don't yet know whether there are exomoons, although there probably are. But the point about these satellites is that they're now pretty well characterized, because in this solar system, we can send spacecraft to go and look at them. You can't do that with other solar systems. And when we look at these moons, it turns out that many of them have oceans beneath their icy surfaces. So Jupiter, discovered by Galileo, has 4 big moons. Saturn has 1 big moon and a bunch of little moons, and Uranus and Neptune have moons also. And the ones which are labeled in blue, we are now really quite certain that they have liquid oceans beneath the surface. So Europa, Ganymede, and Callisto all have oceans. Titan has an ocean, and even tiny Enceladus has an ocean. The way that we can tell this varies from body to body, and there's a lot of research that goes into that, but still, those objects we're pretty sure have liquid water beneath the surface. And so the volumes of water that we're talking about are really very considerable. This is a nice diagram showing the volume of the Earth's ocean water, that's the blue dot on the right, compared to the volume of liquid water on Europa. And you can see that Europa actually has more water, more liquid water, than the Earth does. And so in some ways, you would think about this as really a quite habitable environment. What else do we need for life? Well, Jim talked about this too, that you need to have liquid water. You also need some source of energy. And on these small moons, because their distances to the gas giant vary, they actually get squeezed and stretched by the gravity of the gas giant. And that squeezing and stretching causes heat. If you take a squash ball and you squeeze it, it will warm up. That same process generates heat in the insides of these bodies. And so they may be quite hot on the inside. And so what you're seeing here is an image of what the inside of Enceladus might look like. It's being heated from below, and so you get these plumes of water rising through the ocean. And Enceladus is particularly interesting because it actually has geysers erupting water into space. And so in principle, we could actually fly a spacecraft through those geysers and collect the samples and analyze them. So these icy bodies have at least many of the requirements for life. What we'd like to do is to try and figure out which, if any, of these objects really are habitable. And so the way you do that is you go and send another spacecraft. And so one of the things that NASA is working on very actively at the moment is a spacecraft to go back to Europa and really look at it properly and see whether there are any signatures of life. And so this will be happening in the next decade, and that's one of the things that I'm most looking forward to. So thank you very much.
Astronomy kind of touches on very fundamental questions like, how did we get here and are we alone? And so that really resonates, I think, with everyone who wonders about why we're here. I use models of planet interior structure to try to disentangle the ratios of ingredients or the materials that go into forming planets. And I'm particularly interested in planets that are super Earth and sub-Neptune size. These planets in the size range are intriguing to me because their very nature is an enigma. In our solar system, the Earth is the most massive rocky planet, and Uranus and Neptune are the smallest gas giants at 15 Earth masses or so and 4 times the size of the Earth. But now, around other stars in the sky, we're finding planets that fill in this gap of an order of magnitude of mass for which we have no solar system analogs. And so what are these super Earth, sub-Neptune-sized planets? Are they scaled up rocky bodies, scaled down mini Neptunes, or something completely different? Maybe Kevin Costner water worlds. So in order to address this question, the subset of planets that are detected both in transit, by their shadows passing in front of their star, and dynamically through their gravitational influence on their host stars or other planets in the system, are most valuable. Because with the planet radius measured from the depth of the transit, and the planet's mass measured from Doppler wobble or transit timing variations, together combine to give the planet's mean density and some handle on a planet's bulk composition. So in a similar way that sugar, flour, eggs, and butter are the main ingredients that go into baking a cake, for planets, hydrogen and helium, water, silicate rocks, and iron are the main ingredients. And so if you imagined we had 2 cakes that were frosted, so they look from the outside that they're identically the same size, imagine we were to weigh them and find out that one's much heavier and denser than the other. Well, without actually cutting the cakes and eating it, you might be able to make a somewhat educated guess that, oh, maybe that heavier cake is kind of a dense fruit cake, and then the lighter one is a nice light angel food cake. So we can do something similar for planets. When we measure both their size and their mass, we can try to disentangle the proportion of ingredients from which they're made. We might not be able to pin down their unique true composition, but we can at least try to narrow down the range of possibilities and explore kind of the various proportions of hydrogen, helium, water, silicate rocks, and iron that went into forming the planets. So here I'm showing a plot of measured planet masses and radii. So we have planet mass on the horizontal axis and the size of the planet relative to the Earth on the vertical axis. With exoplanets, we now have several hundred planets with measured masses and radii to complement the 8 planets in our solar system. And so one of the things we've recently learned is actually, if you look at the population of close-in planets, most planets that are bigger than 1.6 times the size of the Earth have low densities. They need these extended volatile envelopes. So if we really want to find rocky, potentially habitable planets, we should probably focus on these little guys. Thanks.
We have a microphone there, so please, if you're able to, please walk over to the microphone to ask your question.
Thank you very much. It's a great panel. I just had a question. With this discussion of red dwarf stars and the habitable zone, various versions of it, that would be around a red dwarf star, and I believe the planets would have to be much closer. So what are the chances? I've heard discussion previously about that those planets might be tidally locked. And so how would that change your thinking about what habitability would mean on a planet like that?
So if a planet's tidally locked and yet still has an atmosphere, then the atmosphere can carry some of the energy to the night side, as long as the time scale for the wind to kind of advect some of that heat around is shorter than the time scale for the heat to be re-radiated away. And so actually, that's one observational approach that people have proposed to try to assess whether some of these planets around M dwarfs have atmospheres or not, is to look, okay, if we look at how their apparent brightness varies as they go around in their orbit around their star, if they're tidally locked, does the apparent brightness as we see different phases of the planet change as we would expect if it were just an illuminated day side and a cold night side, or rather is the planet more a homogeneous temperature around its surface, which could indicate that redistribution by an atmosphere is playing a role?
My field is planet formation, so I think the most exciting thing is trying to understand the diversity of planets that we see throughout the galaxy. In science, it's discovering what you don't expect that usually is the most beneficial. Trying to understand, let's say, planet formation really hits at a fundamental characteristic of human beings, trying to figure out where we came from. As you've heard several times tonight, we sort of understand the initial conditions of planetary systems, right? It's a disk of gas and dust particles being relatively small, and somehow these things come together and coalesce to form the planets that we see. Currently, there is a debate going on in our community concerning the actual process of which that happens. Believe it or not, we really don't understand. There's the classic view of this, where you start off with dust and they sort of stick and grow, and you make rocks and mountains and city-sized things all the way up to objects the size of the planets. And then there's this new idea, which is called pebble accretion, which is based on the idea that objects about this size, meet pebbles, right? Objects about this size do everything, right? We get these things through these early two-body accretion. They congregate near each other due to aerodynamic drag, collapse to form nearly planetary-sized objects right on their own, right? Pluto, for example, could easily be just a collapse of objects this size. And then the larger planets grow by accumulating these final pebbles. So I said, what we do is do large-scale numerical experiments, right? People have been working on the classical model for planet formation for 25 years. Matter of fact, one of the leaders in that field was George Weatherall, if you've heard of him, who was at Carnegie Institution at DTM, right? And no one's really been able to create a system that looks like ours. And what I'm going to show you is a simulation we've done within the last couple of years where we've been able to reproduce the structure of the solar system with pebble accretion. So what you see here is a plot of mass in the vertical axis, right, in Earth masses. So 1 is the Earth, and something like 300 is about the mass of Jupiter. And we start with a population of objects that are roughly the size of the asteroids that we see today. The horizontal axis is distance from the sun, right, in astronomical units. So 1 astronomical unit is the location of the Earth, and you'll see the pebbles stream along the bottom of this simulation as it goes, and watch the planets form. So out in the outside, we see the formation of the giants, and in 10 million years, we end up with a system with the Jupiter mass object and the Saturn mass object, plus a couple of ice giants. In the inner solar system, we end up with the Earth and Venus. Let me just show you the last slide here. So you have Venus and Earth and Mars and the asteroid belt. So this is the first simulation that I know of that can actually reproduce the basic structure that we see. And that's all due to pebbles. Thank you.
I'm really excited about the results that are going to come out of both Gaia and TESS, which are 2 upcoming missions. Both of these missions are going to help us kind of fill out the parameter space for where planets exist around stars other than our sun. And the reason why I think that's going to be as exciting is it's going to really finish our sort of the exoplanet revolution that started 20 years ago.
Thank you very much for the opportunity to speak to you today. It's a pleasure to be here.
And what I want to tell you about is how star formation and planet formation are all connected to one another. What I want to start with here is this is an image taken by the Hubble Space Telescope many years ago. And what you're looking at are really the true birth sites of stars and their planetary systems. And this is millions of times bigger than the scales of our own solar system. But if we want to really understand the planets that we get to at the end of the day, we need to understand these first stages. I like to think of it a little bit like trying to make a complicated dessert, right? We're looking at our solar system today, that's the cake. And what we need to understand is not just the ingredients that we began with, but the recipe that takes us from these ingredients, which is just cold, hydrogen, and a few tiny dust grains, all the way to things like the Earth. And so that's what we're trying to address when we talk about origins. And so one of the things we're able to do now that we've never been able to do before is look at the actual formation of planets. And so what's being shown in this image here is cold dust around a very nearby young star. So that inset there that you see blown up, that's the same size as the distance between our Earth and the sun. And so if we want to understand this process, we have to be able to look at these very, very small regions because we want to see how the gas and the dust makes its way down onto the planets themselves. Now, I've shown you two observational images to start, but I am not an observational astronomer. I'm a theorist, and what I like to do is use computer models to try to put these things together. And one of the real challenges in understanding the process of planet formation is that rocks don't glow very well, right? So if you want to see something in the process of forming, we can either look at tiny dust grains, which is what you're seeing here. And this is one of the real surprises, I think, to many people. If you want to look for growing planets, you can look at tiny dust grains, things that are like dust bunnies under your bed. But if you wanted to look at something like Earth, it's incredibly challenging. And so instead of looking directly for those boring, non-glowing rocks, we can try to look for signatures of the planets in the surrounding disk. And so what I'm showing here is a numerical model of a Jupiter growing inside a disk of gas and dust. And on the left side, what you see is the structure of the gas as it's shaped by a big, massive Jupiter. And on the right-hand side, what we've done is not only simulate how the gas goes around the star, but we've simulated how the dust interacts with the gas. And gas-dust interaction is one of the most complex, fascinating parts of understanding planet formation. You can think of it as not so different from a bicycle peloton, where being kind of hidden behind another biker can help you as you orbit your star. And so what we're trying to do is simulate this dust and then imagine what it would look like as observed with one of these telescopes in order to see whether or not we might be able to see these kind of signatures and infer what kind of planets might be hiding. And so this is one way, again, we can get directly at the recipe, not at the end product or the initial ingredients. Now, in the last 10 seconds before I go, I have to tell you that my colleagues have been hiding a very dirty secret from you. And that is that stars are not always by themselves. In fact, half of stars like our sun come in pairs, or as this image on the left is showing you, triples. So that means there's 2 or 3 stars that are all orbiting around them. And as this movie is showing you on the left, we've even discovered planets in these multiple systems. So Tatooine is no longer the realm of fantasy. We know these systems exist. And if we want to understand planet formation globally, we can't ignore these systems any longer. Thank you very much.
We've heard a lot of discussion this evening about how solar systems form. How about how they end, or how they continue to evolve toward an end or some equilibrium situation that would persist in the event that there were not a catastrophic event in the central star?
So we know that stars like our sun don't live forever. And at some point, they will run out of hydrogen in their cores to fuse into helium. And then they will eventually turn into red giant stars, which basically puff up and become maybe 100 times the radius of the current sun. And so what we think will happen is twofold. Some of the planets are going to just get eaten up because the star is going to grow and engulf them. But there's another funny thing that happens that's kind of cool, which is that as the stars puff up, they also start to lose mass. And so they get winds that causes mass to kind of fluff off those surfaces. And as they lose mass, they kind of start to lose a little bit of the hold on their planets. So the planets can actually start to move out. And so it's not so easy to figure out which planets are going to get eaten and which planets are going to kind of move out. And a lot of people now are looking not at stars like our sun, but looking way in the future to the end products of stars like our sun, which are called white dwarfs. And that's sort of the dead core that's left behind. They're tiny things with almost as much mass as our sun today, but maybe the size of Earth itself. So they're really, really compact. And what we can see is we can see evidence of rocky stuff having been thrown into the upper atmospheres of these white dwarfs. So we can detect things that look like asteroids and Earth-like planets by looking at the lines in the spectrum of dead stars. And what this is telling us is that not all the stars just simply get obliterated, not all the planets get obliterated by stellar evolution, but that some of them may get kicked onto crazy unstable orbits that fling them into the end product, that dead star. And we're actually able to say something about compositions of planets by looking at these spectral signatures that otherwise we would never be able to do. Leslie talked about, cutting into that cake. This is one way we actually can cut into those exoplanet cakes, is by looking for these signatures in white dwarfs.
The question that I'm particularly interested in is, will other planets have the same composition that the planets in our solar system have? And you've heard a little bit about this already today in terms of water and other materials. So this is what I mean about creating a timeline with the natural laboratory of the young stars on the sky. And so from left to right on the diagram I'm showing you are stars of different ages that all have disks of dust and gas around them that are the sites, we think, of planetary formation. On the far right, maybe one that you recognize, that's our solar system, and you're looking at just the very tiny remnants of the disk that we have created by the evaporation of comets in our solar system. So on the left side, you have all the raw materials you need for planets, and on the right, just a little bit of the tail of the distribution that tells you maybe what those original bodies were made out of and what any planets that did manage to form are getting their volatiles or compositions from today. So the question that I want to ask is, where are the materials necessary for life? As Jim said, we know we want carbon and oxygen if we're going to have life like ours. So let's start with oxygen, and in particular, water ice. So this is a set of images of a disk that I made with our Carnegie Observatory, the Magellan Telescope. And the way you're seeing it is with starlight reflected off of dust grains. So imagine you're sitting by your sunny window on a sunny afternoon. We could use another one of those here in DC. And you're seeing the sun come in and glint off of, at least if your house is like mine, a little bit of dust in the air that you can kick up. Well, that's what we're seeing here. You're seeing dust that is glinting in starlight. And we cannot just look at its glint, we can look at its color. And so what we do is we measure how bright this disk is as a function of wavelength. And you can see there are 4 wavelengths plotted up here, all in the infrared part of the spectrum, so you wouldn't see it with your eye. But we can ask, how bright is this disk? And you can see it's pretty bright at all wavelengths, except for that one in the upper right that I've labeled ice. And you can see that on the plot as well, that the disk gets faint at that wavelength. And that's because that sunlight hitting the disk is being absorbed by water ice grains, and it's not being reflected back to us. It's been very hard to find water ice in disks. We think that's because mainly it's being used to build up planets. But this is an example of where we know that there's copious water ice in the outskirts of a disk. So let's go a little bit older. What happens later in the evolution of a disk? And so these are images of older stars, where now most of the gas is gone, and we're left with just belts of asteroids and comets like those in the solar system. And so the white contours there show where those bodies are, those asteroids and comets, and the red images from the Hubble Space Telescope underneath show where all the dust grains go when those asteroids collide and those comets evaporate to make small things. And these look amazingly similar, right? Incredibly alike, except one of them is actually very different from the other. The one on the right actually has copious amounts of gas. It's as if multiple comets were evaporating and colliding every second. And so I like to imagine that any planets forming within that disk could look very different in their composition for carbon and oxygen, the gas that we see from the comets, than any planets on the left that are forming in a system maybe mostly made out of dry asteroids. Thanks.
Thank you, Alicia.
I'm going to apologize if you've already addressed this, but I missed it. So I'd like to ask if anybody can just tell me really simply what is dust?
It's exactly what you think it is. Imagine the dust bunnies under your bed, at least my bed. I don't want to insult your bed. We're a ground up rock. Pick up any rock you like on Earth and grind it into very tiny particles, a micron to 10 microns in size. Imagine chopping up a rock into that, and that's what we mean by dust.
We're at a really interesting time because we have astronomers who are making these incredible observations on things that are happening in space, in young solar systems, and we also have great things happening in the lab. Samples from different parts of our own solar system where we can bring them into the lab, measure their chemistry, measure their age. And for me, the most exciting thing that will happen in the next decade is really bringing those two things together, to really untie the knots of the most important scientific questions about how our own solar system formed by bringing all of these observations together. I ask two basic questions: how much water and what kind of water? And so this presentation is a small section of that. The movie that you're watching right now is brought to you by the fine people at NASA. What you're seeing is a snapshot or a simulation of how we think our own solar system formed. Today, of course, we have a variety of planets of different sizes with different amount of rock and gas orbiting the central star, but this is not how everything started, right? The solar system, we think, started essentially as a cloud of gas and dust that was somehow brought together in a certain part of our galaxy. And once this cloud of gas and dust reached a critical mass, a star was nucleated. And once the star was nucleated, the gas and dust expanded. And as this happened, there were pits of gas and dust that began to accrete together into the individual planets that we see today. Of course, I want to know in this system, where is the water and what kind of water are we talking about? So in the outermost parts of the evolving solar system, we think that water had a very special ratio of its two isotopes. So like a lot of elements in the periodic table, hydrogen has two isotopes that have the same number of protons, just one proton, but they have different number of neutrons. So hydrogen of mass 1 has only a proton, and hydrogen of mass 2, which is called deuterium, has a proton and a neutron. And the ratio of these, the relative amounts of these two isotopes is really, really important for determining what kind of water came from different parts of the solar system. Of course, the sun has most of the mass of hydrogen in the solar system. It's 99.9% of the total solar system mass, so most of the hydrogen is in the sun. But the sun has very, very small amounts of deuterium. But at the same time, comets that are formed very, very far out in the solar system have fairly large amounts of deuterium, roughly 4 times the amount of deuterium that is in the hydrogen that makes up the sun. And we think that in this diagram where you see sort of a red inner part of the solar system and a blue outer part, we think that these two different reservoirs of hydrogen were somehow mixed. We don't know exactly how, and we don't know exactly when, but those are really two very fundamental things that my research is trying to address. And we address this by taking samples of some of the meteorites, bringing them into the lab, taking them to our scientific instruments and trying to measure how much water is there and what kind of water. How many of these two isotopes of hydrogen do we have? And we hope that as this research continues, that as we continue to study water, its isotopes, and also the isotopes of oxygen, we think we can begin to piece together, along with the ages of different planets and different meteorites, the evolution and the time line of water delivery, beginning at the very earliest parts of solar system history and continuing to the present day. Thanks.
Hello. I am incredibly excited about the prospect of finding life on planets orbiting other stars. But I'm also worried that nature is going to be more creative than we are. That processes that are physical and have nothing to do with life will create signatures that mimic what we expect life to make, or that life will be more diverse than we expect, and it will create signatures that are entirely unexpected. So what I'm interested in doing is understanding the diversity of planetary systems that you can create just by physical processes. What are the physical processes that generate the kind of planetary system around a particular star? Then we can go look at the weird ones, and maybe that's where life is. So for today, I'm just going to talk about composition in the simplest way. Ultimately, we want to know details about what planets are made of. But right now, I'm just going to talk about what's known as metallicity. So on the bottom of this plot is iron divided by hydrogen. So you should just think of this as how much solid material there is compared to the gas that ends up in the star. And this is one of the headline early results of exoplanet observations. It shows that as you look across to the right-hand side, all the numbers go way up. So you have more solid material, you make more planets. And that seems very sensible. But does this actually mean that we should search for Earth analogs around high metallicity stars? And since I'm asking, you can probably guess that I'm going to say no. So why do I say no? So let's take a look at this in a little bit more detail. And I'm going to show a few plots here. And on all of these plots, blue means high metallicity stars, and red means low metallicity stars. So here, what I want you to do is look right in the middle there in that gray part at the bottom, and you can see this big clump of blue dots. And what those are is sort of down on this plot means that a planet has a really eccentric orbit. It's really oval. So it gets really close to the star and then far away. So what those sort of middle blue low down dots there are giant planets that are orbiting at distances similar to Earth around their stars, but they're on really eccentric orbits. So if you think about it, this is a really horrible place to look for a planet like Earth, because if there's an Earth there, it's going to be kicked out by this Jupiter that's orbiting around. And even if that Jupiter has a moon that might be like the Earth, it's going to be toasted as it gets really close to the star, and then it's going to get cold as it gets far away. And it's not going to be a nice place to live. All right. Okay, so let's look at this a little bit more. Now I'm going to take a look at radial velocity detected planets. And here now this is a distance is going across, and then going up is the mass of the planet. So we have some blue points here. These are high metallicity stars, and you see sort of a big swath of planets. And if you look up at the top where the highest mass planets are, it seems like they go across a range of distances. But now if I switch it to low metallicity stars, that's not true anymore. You know, on the left, close to the star, there aren't very many. I'll go back and forth. You don't see that big swath going across. You see a big uptick, at larger distances where we think giant planets might form more easily. So if we put these together, you can see that these close-in giant planets, those ones that were in that headline early result, because they're the easiest ones to see, are more likely to be around high metallicity stars, but they're really not the nicest place to find a planet like Earth. So can we put this together? And here's an example of how we might do that in maybe the most simplistic possible way. Let's make a cartoon. You have distance from your star, you have your disk mass, maybe that's set by your metallicity, how much solid material you have. On the bottom here, you make in the brown rocky planets and ice giants, and as you go up, you start making this red set of gas giants. You have really high, and now you start getting dynamically mixed orbits because you make so many gas giants that they start mixing each other. And sort of amazingly, this simple picture can't immediately be ruled out. We can put systems on this plot, and they sort of work. So this is the sort of thing that I'm trying to do in the hope that we can find the weird planets that might host life.
Thank you, Ray.
It's obviously natural that when humans begin to look for life beyond Earth, that we would look for life as we understand it. Do you think we're limiting our search by looking for life as we understand it? And I guess specifically, why are we so sure that life must be carbon-based?
So can I just say briefly that there are good reasons to think about carbon, and I'm sure someone will talk about them. But I actually really agree with you. This is why I think that we really should understand the broad range of physical processes that create planets that don't have life on them. And if we can understand that well enough, we can really identify what's weird and what's odd, and then think really carefully about whether there might be a kind of life that could produce that, whatever that is. Because I think usually the universe is more creative than we are. And even if we can come up with fantastic reasons why life can only be carbon-based, I'm still not convinced.
I do agree that we should keep our minds open, and we, as an observer, I do like fishing expeditions. Go and see what's there. Measure what's there. What gases do we find in the atmosphere of a planet? Does it look like we expected or not? We love it when we come up with surprises and things are not as we expect them. And so I do think we ought to design our experiments to be as broad as possible, to open ourselves up to the most amount of discovery that we can manage. And then we have to figure out what that means. That's the challenge that comes with being open to exploration.
We like to visit new things, new places, to imagine them, and planets are essentially places where you could imagine yourself walking around or exploring. But I think the sense of exploration is here the key.
The question of finding life and finding planets elsewhere has changed from a philosophical point of view to some practical questions that we can address. So first, let's review very quickly why finding planets is hard, what it took so long to find them. People have been looking at them for centuries. Basically, we are going to try to see a planet around this star in the center of the image. This is Tau Ceti, and we take our telescope in the backyard and try to zoom in, and this is what we get of the star. We don't get a point source. What we get is a blur of light that's coming from the star, and around this star, somewhere, there's a planet orbiting it. And do you see the planet here? I don't, right? So I'll zoom again, and you see something in the center. That's the planetary system there, and we zoom in again. We see what would be the Earth orbit around this star. The star is still at the center, but our telescope distorts the light, the image, so we get all these blurs. So for each photon that's reaching us from this planet, we get 10 billion photons coming from the star. And we have to separate this light to be able to eventually measure things from the planet, not from the star. The stars are interesting, but today we talk about planets. So how we still find planets, even if it's so tough? We have found 3,000 of them. What we have is a method. There are two methods, basically. They are called indirect methods. We don't measure. We don't see the planets themselves. We see what the planets do to the light of the star. One method is called the transit method. The planets, some of them, go in front of the star. So we see a reduction of light as the planet crosses in front of it. It repeats. So from that, we know the orbital period. The other method, it's called the Doppler technique. And what we do, we measure how this star is moving. And from that motion, we know that there's a planet orbiting it with the same period as the motion. The more massive the planet, the easier it is to detect the planet. Now, these methods have a problem that can detect planets very closely into the star. It's easier to find planets that go in front of the star if you are looking at planets in very short periods. That's what the Kepler space mission and other surveys have found, that most planetary systems don't have solar systems like our own, but have tons of small planets in very short period orbits. This might seem a problem, because in our solar system, these planets would be too hot to host life. But, for example, we have certain kind of stars that are not as bright as the sun. They are called red dwarfs, or M dwarfs. And actually, these red dwarfs constitute about 60-70% of the total number of stars in the galaxy. In our solar neighborhood, here you can see 400 stars. These are the 100 nearest stars. And from them, there are 400 regular stars, maybe 20, 30, 50 solar analogs, but most of them are red dwarfs. They have an advantage, is that because they are smaller and we don't detect the planets directly, we see the effect of the planet on the starlight. It's easier to detect in both transit and the radio velocity technique. And there's another advantage to detect these planets that might be similar to us. These stars are fainter, and therefore these close-in orbits are not hot as they are in the solar system, but they have temperate temperatures, even if the orbital period is only 20 days. Mercury has an orbital period of 90 days. So we have these planetary systems with 2-3 Earth-sized planets, very close in, that are in temperate orbits, even though they are in very close in configuration. So this thing, it looks like something that some of you might have heard. We just learned this in the last 4 or 5 years, thanks to Kepler and some other surveys. So these red dwarfs, Earth, is where we are now really starting to look for traces of maybe molecules or things, and I'm going to show you in a second how we do that, or how we are planning to do this. For this, we have these very nearby planets. I was involved in the discovery of Proxima b. That's a red dwarf star, the nearest star to the sun. It has a planet similar to Earth. But another example are the TRAPPIST system that has 7 Earth-sized planets, 3 of them in these warm orbits that could contain water on the surface. So with these planets, the idea is that because the star is smaller, we can also see the effect of the light going through the atmosphere of these planets. That will tell us, when they go in front of the star, if there are molecules. We can do that with James Webb Space Telescope. It has been done already a bit. Some preliminary work has been done with Hubble. But this will happen in 2-3 years. We will be able to start probing the atmospheres of these planets that are transiting in front of these red dwarf stars. In 10 years, with giant telescopes, we will have the capabilities to start separating the light from the planets and the star and plug in spectrometers to these giant telescopes and eventually have space missions that can really separate the light, like LUVOIR or HAVEX, when we have 10 or 20 meter class telescopes on space. And then if we are not satisfied with this, because what we will see as evidence for life will be these very sketchy things, not the fancy things we expect to see, then if we want to have something else, we are not convinced that this evidence is conclusive, the next step would be to build 10-kilometer sized telescopes if we really want to have images of these things. So for now, in the next 10, 20 years, we will have to examine these planets, detect molecules, and try to figure out if this is really evidence for life or not. And this is where we are at this point today. Thank you.
Thank you, Guillem.
Yes,
thank you.
I was just curious, we're kind of familiar with our friendly little neighborhood solar system, and we're looking for these exoplanets at such mind-blowing distances. And do we have any sense of what our little solar system would look like from those sort of distances? Would we have a sense of this being a habitable planet if we sensed it at the same distance that we're trying to look at these solar systems at?
Wonderful question.
So from our solar system, and other people can comment on this, we could be, nowadays we would be able to detect Jupiter and a bit maybe Saturn if we were lucky. Maybe the Earth would be transiting in front of another, if we look it from the right angle, but detecting Earth and being confident of that detection with current technology would be very hard. So basically we would see very little, very few hints that our system is inhabited. We would see that it has this Jupiter long period gas giants that it's not really clear if they are really crucial or not for the emergence of life. But that's all we could tell, probably, looking at our system from the distance.
Right now, we have the James Webb Space Telescope is going to be launched. It's going to allow us to see young stars and planet formation taking place at scales we've never been able to see before. There's no shortage of new things to discover and to think about. Rather than looking at stars and trying to find the planets, I asked the question of where should we be looking? It's hard to, as we heard about, to find these things, and even harder to characterize them, to determine whether or not they're habitable. But if we know how habitable planets form, if we can understand what are the processes that determine whether a planet that eventually forms is going to have the properties that allow it to be habitable, perhaps we can then target our stars better, identify where to look, and save ourselves some time. So what I do is I study planet formation. I say I do it from the micro to the macro scales, and let me explain what that means. Our general framework for understanding how planetary systems form dates back hundreds of years. It starts out with the ideas of Laplace and Kant, who said that clouds of dust and gas collapse to form stars, and around those stars we get disks, and those disks provide the raw materials from which planets form. Now, those disks contain small dust particles that over time grow larger and larger to the planetesimals, the embryos, and eventually the planets that we see. And this framework has not really changed all that much, but as scientists, what we're trying to do is fill in the details, understand when does it happen, what are the variations that we can expect. And so we study these things in greater and greater detail to provide those answers. Now, one of the ways that we can go about doing this is turn our attention to our solar system. We know we have a habitable planet here. We have a lot of information about what this planetary system looks like and what the properties are. But there's a particular group of objects, the asteroid belt, that ranges between Mars and Jupiter that contain leftover building blocks from the planets. Everything that went into forming the Earth got baked at high temperatures, and its original properties have been destroyed. But these asteroids provide a record of what the original building blocks were like. Now, fortunately for us, nature provides samples of these objects on a regular basis. There was just a meteor that entered the Earth's atmosphere in Michigan. Got a lot of news in the Chicago area. They went out, the Field Museum found it recently, and we've been studying it in Chicago. But there's other places on Earth where we can go find rocks. For example, in Antarctica, we find them in the open desert. And they stick out, we collect them, and we bring them back to a lab, and we can analyze them. We can look at them, and what we're basically looking at are time capsules from the very earliest stages of planet formation. These are the building blocks of the planets that we can pick apart, we can study on the scale of microns, millimeters, and understand what are the elements, what are the minerals that make these things up, and how do they relate to the planets that eventually form. So we can use this and understand how things varied on the scale of something that fits in the palm of your hand. Now, within our solar system, that gives us information about what happened in our solar system. But we know that planets exist elsewhere, and that's ultimately where we're looking for these other habitable planets. So given that the same framework is expected to apply for planets around other stars, we can start to ask, what are the differences that we expect to see? How do things work in other systems compared to what we have in our own solar system? So with that, what we can do is take the astronomical view. We can point our telescopes to regions where stars are being born, because planets and stars are born together. And in certain regions, this is the Orion Nebula that you're looking at, we can look at and characterize what are the stars that we see and what are the disks like that surround them. So we're actually looking at what we think are analogs for the early stages of evolution for our own solar system. Now, they don't give us the same information in terms of scale. What we're looking at when we see one of these disks, when we see a star surrounded by its disk, we're looking at things that span 100 astronomical units, 100 times the distance between the sun and the Earth. So seeing things on very fine detail is difficult, but we do see structure. We do see the type of environment in which we think our solar system may have formed. So by combining the data that we have from astronomical observations, by combining the information that we're able to pick apart from cosmochemical studies, what we're working to do is build a coherent and grand picture for how planetary systems form and understand what are the differences between what happened in our solar system and what may be happening around other stars, and iterate to basically try and understand where might habitable planets be found. Thank you.
I'm trained in chemistry. I've spent my life thinking about the periodic table, so that's the origin of my question. My curiosity here, and maybe it's another one of these talks, is about the periodic table and how it would look in our universe over time. Because, as I understand it, in the earliest phases of our universe, there were only two elements, basically, hydrogen and helium, and maybe a little lithium. So that was the periodic table in the first million years, maybe, or I don't know the details of how people have thought about that. But could you tell me how many times star systems, star clusters, or galaxies had to go through an evolutionary process in order to get to the periodic table that could create our solar system? Was it one generation, two generations? I haven't ever read about it or had anybody explain it to me.
Well, it's an excellent question, and I would say it's hard to completely answer, but the key is what you said. You know, everything above hydrogen and helium that we have, that we're walking around, was fused in stars. We are stardust, as Carl Sagan said. How much of that was produced in different stars is to be debated. A colleague at Carnegie, Connell Alexander, one thing that you can do is look at the meteorites we have, and you can identify grains within those meteorites that formed in the atmospheres of dying stars. And based on his estimates and based on the statistics, he argued, I believe the number is that something on the order of 60 different stars had contributed material to give us the heavy elements beyond hydrogen and helium that we have in our solar system. Now, whether or not that's typical for other star systems is another question. But we do expect that over time, as our galaxy has evolved, more stars are dying, more material is being ejected into space. So the metallicity that Ruth had talked about continues to increase for later generations of planetary systems that form.
I mean, I can add to that a little bit. One of the things that Connell Alexander also demonstrated, along with one of his colleagues, is that there are certain isotope ratios in some of these pre-solar grains that are thought to actually record the evolution of the stellar compositions as they evolve over time, and in our local part of the galaxy, and indeed in general over the age of the universe, these isotope systems have continually changed their composition, and can actually be used to try and estimate how long it has been since the Big Bang. One of the advantages of working on the hydrogen isotope systems is that we know that for example, that except for rare cases, deuterium, the heavy isotope of hydrogen, was really only made in the Big Bang. And so stellar processes never make deuterium, they only destroy deuterium. And so this is one isotope system that's actually very sensitive to how many stellar cycles that we have undergone in our local part of the universe and throughout the universe.
Yes.
A question: is it possible to detect free oxygen
in the atmospheres of any of the extrasolar planets? And if so, would that be definitive for life?
So not right now. No one has detected, and by free oxygen, we're really thinking about molecular oxygen. No one has yet detected molecular oxygen in the atmosphere of a Earth-like planet. In fact, we haven't even detected atmospheres of Earth-like planets yet. But our simulations show that the next generation of large ground-based telescopes can do exactly that. And that's one of the reasons we want to build like the 25-meter telescope that Carnegie is involved in building, because we want to do that experiment. We want to look at nearby planets about the same size and mass and temperature as the Earth and look for molecular oxygen. However, we don't think that that will be definitive proof for life. So it turns out you can make molecular oxygen without biology. And so the things that we think would be definitive for life would be a combination of molecular oxygen and some other molecule that molecular oxygen reacts with very strongly. Because if you see those two things simultaneously, you know they have to be generated all the time. And that kind of generation is more likely to be life. But again, we should be creative, and we should think about all the amazing things that our geologically active planet does to produce molecules, methane, carbon dioxide, carbon monoxide. And whenever we do first detect those molecules that we associate with life, we're still going to have to be skeptical and creative about thinking about what other ways they could be made.
I was just wondering, what is the difference between the dust that made up the rocky planets and the dust that make up the gas giants and icy giants?
That's a great question. As you go, we don't know the full answer to it, but one answer is that as you go farther away from your star, your disk gets colder and colder. So if you're close by, you can't keep water ice solid. And so the Earth is not made of balls of water ice. The water was in the gas. If you go out far to where Uranus and Neptune were made, it's very cold. And so water is solid, and a large amount of their solid composition is actually made of ice. When you're talking about gas giants, then Jupiter is actually 95% hydrogen and helium. In many ways, it's much more similar to the sun than it is to the other planets. So, and in fact, if you look at Jupiter and you think of it as just a mini sun and put its Galilean satellites around its moons going around Jupiter, it looks like its own little solar system.
Well, these have all been wonderful questions. Let's close out the evening. Thank you.